Hello everyone, this is the LibHal bi-weekly meeting. It is August 18th, 2026, and I have a little bit of an update. Simply put, if you've been using the old slides for libhal to kind of look at the old documentation, I've split them. I'm going to start doing them by year. It does make it a little bit more complicated in order to find old information, but I think having it per year should be pretty relevant. I might even make it per every 2 years. The previous one was all the way from 2020 up to 2026, and I was about to get to 1,000 slides. And every time I open up that presentation, the amount of RAM that my computer uses up is quite big. So I'm trying to split them up. Anyway, it is August 18th, 2026, and here is our agenda. So it's actually been a while since we had our last meeting. I think it's been at least a month. I've been on vacations, multiple of them, so I've been a bit busy with that. I'm also getting ready to be teaching at San Jose State University in the computer engineering department for the intro C++ class, as well as the one of the light classes you take, which is Introduction to Embedded Systems. But a couple things that I've been able to get done have been, and a lot of it's been porting work. And I want to be actually upfront about this. A lot of the porting work was done through coding agents, mostly Claude, but I've been trying out other agents like Google Gemma and Quinn and other things like that. But I've been looking at all the code, read everything. So if there's any issues, it's probably just my fault. For the agenda, we have libhal-usb. This is really just taking the USB drivers that we had in libhal-util and bringing those into libhal, into its own repo. Madeline and I were back and forth. Madeline, the other person, if you have not heard of her name before, Madeline is the other person who was working on USB, and I think also Milo as well. We all kind of, at some point, probably talked about the idea of having, either a repo or just simply asking the question of where exactly should this particular driver go. And over time, I've realized that it's probably just best just to throw everything into libhal-usb. That isn't what's bolted into libhal itself. It's still a work in progress. I need to get it working completely fixed up. It's going to be libhal v5 native, since the v4 one's already embedded into libhal-util. There's no reason to kind of bring that over as well. And that's pretty much all we're going to talk about when it comes to libhal-usb. It's pretty much all of the same code from before, just with the libhal async APIs where necessary. We're going to go over a couple libhal v5 updates. Then we'll go over a v5 VTABLE optimization that has pretty much been like a free lunch this entire time once we figured out what it was. So I'll talk about that. Then I'll also go over the libhal v5 migration blockers. So a couple of things that are preventing me from making further progress on the libhal v5 port. There's a few things, and they shouldn't be too hard to do. Just, it takes a little bit of time. And then finally, we have libhal v5 port for libhal-util, and then also for ARM-mcu. I'm just going to we're going to do a bit of an exploration through that. So first up, let's look at the libhal v5 updates. There were a number of things that I've updated with libhal v5. I think I kind of missed a couple of them, but for now, we're just going to talk about these ones. The main one is the introduction of the pimple type. In the last time we had a meeting, I talked about how this was tentative. Now I've kind of made it not just tentative, but implemented it. What you do is you create your own class. So this is something that we'll expect from other drivers. If you have a driver that is a composite or a manager, that when I say composite, I'm really just saying that whatever device you are operating over, there is a multitude of things that it can implement. For example, with a smart motor, it may implement a VEL-TOR servo, a velocity and torque capable control servo. It may also be able to be a temperature sensor because it has a temperature sensor internally. It may also have a current sensor and those kind of things. So if you have some object that can be multiple things, it may also have some implementation details that you want to be able to flexibly change over time without causing any sort of ABI breaks. The pimple class gives us this. I'll show in the next slide how you implement the struct here. But here you simply have to define and declare, you have to just declare the struct that will exist elsewhere within this object. And because it's in this object, it will be smart motor : impl. You'll see it later. We'll have factory functions for creating the object, and then we'll also have some acquisition functions for acquiring those resources from that object. Um, I've also made a bit of a change. This is more of a slight policy thing, but I think in general, um, we can probably reuse the same allocator used to create the smart mode or whatever this object is here for this. So if you add another allocator, it might be, try to make clear if this is allocating the object or if it's just being used for something else that the Veltar servo needs to allocate. Um, yeah, that's pretty much the Pimple template from like the declaration side of your class. Internally, you would, let's say, okay, so the last one was smart motor, but in this case, I borrowed from SPI since I had it fully implemented. The smart motor example came from the previous slides where I was kind of making something a little bit more, a little more generic. So here we have SPI impl. You pass in a couple of fields into it and it sets itself up. It also has a async mutex to be a bus lock for SPI. We have the create function here, which takes an allocator and a peripheral. In this case, it just returns back a pointer. It doesn't need to do anything async, so it just returns back the object. And then here we see Pimple being initialized, where you need to pass it an allocator, and then you need to pass it in all the arguments that'll be fetched. I'm sorry, not fetched. That'll be passed into the impl here. So it's similar to the make strong pointer, where the first parameter is the allocator, and the next set of parameters are all the constructor elements or constructor parameters. Those all, everything after the parameter here gets put into this constructor here. And the rest is just the typical things that you need to do in order to initialize the SPI peripheral. And that's pretty much it. And here's the factory, and you can see the constructor here. Okay, so there was a bit of a change that I realized today. I made the change today as well. It didn't take very long. It was a very simple regular expression change. And the story is kind of interesting. Basically, I was looking at a ISO C++ committee paper, a proposal of some sort, in order to, I believe, make destructors by default no except true, or maybe that was only for deleting destructors or deleting operators. Anywho, I noticed that there was a destroying delete tag, and I was like, oh, I think I have an idea of what that does. So I looked into it. And then from there, I started asking this question I ask all the time, which is are my interfaces optimal? You know, is there something that I could change in them? Then I thought to myself, what do I do for the destructors, the virtual destructors? I was thinking about how they were used and whether or not I ever even touched them in my code. So did some thought, looked around a little bit, and then decided to ask Claude to see if it had any additional information about this. And it pretty much looked into it and said, oh yeah, you have no reason to keep a virtual destructor. It's only really useful if you have places in your code where you have a pointer to a base object and you're going to delete it from there. This ensures that the delete operation makes its way all the way to the base, from the base all the way up to the more concrete class. We never do this thing though. We actually sidestep this completely throughout all the code. We never actually use the delete keyword ever. And because of that, I realized that we don't actually need all of those extra VTABLE entries. We don't need a VTABLE entry for the virtual destructor. So I've gone through and I deleted all of them. This comes from Herb Sutter's virtuality. A base class, and this is actually just good information in general, I believe. A base class destructor should be either public and virtual or protected and non-virtual. It has to be public and virtual because if it's not public, then nothing can access it. And if you're going to try to delete it, you will need it to be public. If it's protected and non-trivial, it means that your normal code, like let's say for an abstract class that cannot be constructed, if it was protected, it means that an object that inherits from that object, from that base class, can access the destructor, and therefore the object can be destroyed. But for the base class itself, it basically ensures that the base class can never be constructed because you couldn't delete it at any point. You couldn't destroy it. You can make a pointer to it. Then if you try to destroy that, that would be a problem. But yeah, virtual destructors are only really useful for deleting an object via its base class pointer, something we do not utilize at all. And then here's the link to the quote that's up here and the rest of the article. Yeah, so for all the V5 objects, I've went through and deleted their VTables. Their destructors. I made them default, and protected. So now they're pretty much empty. Now, if you attempted to do something like this, there's a delete pointer here, you'll get an error like this. That basically just tells you that, hey, error calling protected destructor of class SPI channel, which does not work. And what we're really looking for, and even though it might seem a bit small, and to some degree it is small, but it adds up. In V4, with all of our virtual destructors, we have, this is kind of shows the how much memory gets taken up in the VTable for all the content. So the VTable will contain a number called the offset from top. This is how objects with multiple inheritance can determine if they are the first or second or nth number inherited object. And that just allows it to figure out where it is relative to the actual object and then move its pointer to that point. In general, this is almost always 0 for all of our objects. Then we have a pointer to RTTI. This is almost also always 0. So these two fields are almost always 0. And then these two, which are the complete object destructor and the deleting destructor, these came from the VTable. And unlike other VTable entries, the destructor actually puts 2 entries into the VTable, not just 1. And then anything that I say implement, and anything after this, which is all the interface functions, those go afterwards. So this would actually be a ... here to say like there's n number of those. But this is basically the overhead. So before it used to be 4 pointers or 4 words. Now it is 2 pointers, which halves our overall overhead for these objects. There's also one other benefit, which is that there's a good chance that the complete object destructor and deleting destructor weren't the same. Now, from this example here, I do believe they are the same. And actually what I'm going to do is I'm actually going to open this up. And I hope this is still being captured right now. And basically what I want to show is that we have interface A and interface B, and then a driver that implements one and a driver that implements the other. Now, unfortunately, interface B just doesn't get a VTable. It just doesn't show up here. Probably because it's being optimized and inlined. I tried to get rid of that, but it seems like it's not really working. But we can see the VTable for A, which includes 2 destructors. Now, luckily, they both point to the same exact thing. But there's a chance that if the class had a deleting destructor, this would have a pointer to that. Now, luckily, because of these being identical, it does mean that you only pay for the destructor that you already had. Like the driver A destructor had to exist regardless. So it will still be something that gets pointed to. Whereas, the driver B is completely eliminated. So I don't know if the driver B constructor would even have existed. I don't think it would have. But yeah, so that's just a little bit of what goes on here. Let's get back into it. Alrighty, let's make sure. Okay, still recording, great. All right, so actually I moved to the next slide, which is basically just me talking about the goal driver object overhead. So the main thing is I've been thinking a lot about, as I create all these different drivers that have basically all these other bits of overhead, I have to ask myself, is it worth it? And how much memory are we going to be using up in the end of the day? And also, how many interface implementations do we expect in a typical binary? These are questions that I've been asking myself a lot, but I always know that no matter what answer I get, having a smaller object size is always kind of like a preferred thing, unless it like removes a capability that we really care about. So I should have actually had a section here that showed what we have currently. These are basically where I want to get in terms of overhead. So we have a little legend here. Everything that's inside of this kind of orangish brown tan colored square is part of the strong pointer control block. This contains the allocator, the destroy function, so it knows how to destroy the object when it's deleted, the strong and weak count, and a VTable pointer. I'm sorry, the VTable pointer actually should not be a part of this control block, so that's actually a mistake. Apologies there. This actually should be, in my opinion, object contents, so it should be actually gray. So the strong pointer part of the equation is only around 3 words on a 32-bit system. So that should only be about 12 bytes. Then the VTABLE is 4 bytes. Then we have an implementation pointer. So when we have a hidden implementation, we use the allocator to allocate it, and then we need to save a pointer to it so we know how to delete it later using the same allocator that was in here before. Yeah, that's part of the bit of the overhead. And after this is basically everything else that goes into the implementation contents. Now, technically, there's a bit more memory that could be here. This could be any information within the driver that is not part of the impl. But I kind of just threw all that into whatever would be the impl contents because effectively it's kind of the same thing. But really, the overhead is this section here. We have 1, 2, 3, 4, and 5 words equating to 20 bytes in total. And it looks like I spelled bytes wrong because I need a T there and a T there. Anyway, this is achievable. I have an idea of how to make this happen. Technically, right now, what we have is actually far worse. We have, these are actually 2 words. We have another pointer in here for the enable strong from this, which ends up equating to around about 1 word, 2 word, about 28 bytes. So about 7 words in total. My hope is get from 7 words that we have currently down to 4 words, 16 bytes, and that would be the cost per driver that you have inside of your inside of libhal. Although some drivers may actually be less than this. For example, they might just ignore having an impl, might not be pimple, and will just be VTABLE and whatever contents they need on the inside. So that's the driver overhead that I'm hoping to get to. And then that'll save us a bunch of memory and RAM. None of this can be put into ROM. This has to be put into RAM. So, yeah. Okay. Before I start getting into like what the code kind of looks like and how it's been looking like with the port, I'll talk about a couple of the migrations that are a couple of the blockers for migration. So supporting multiple tasks and demos. I realized with USB, I was getting all the demos ready and I was like, cool, things are starting to come together. And then I hit USB and I was like, yeah, USB needs to like pull the USB task. Then I realized, how do I want to go about doing that? And I'm not entirely sure. And it's not like it's an impossible thing. I could just make another API called application task 1. But then I realized that I need to have that for all the other demos. So I was thinking about using a weak function that implements nothing, that doesn't do anything, which does kind of work, but module's getting a little upset, and I can get around that. I'm trying to think of what's like the best clean way to make the ARM-mcu demos work in this way. Note, though, that I don't recommend that ARM-mcu demos be an example of how you should write your own demos or your own applications. You have a lot more freedom as to how you want to go about managing all of the tasks that you're going to be doing. Anywho, that's one of the big questions that I'm trying to, I haven't spent time thinking about, but I want to answer before I move forward. Also, another thing that needs to be done is that I've noticed that as I've been porting the code over and looking a little bit at it, I realize, there's some race conditions with interrupts here, and that's a problem. So I was working with Claude, and Claude's like, we could use a critical section, but then, that goes against one of your philosophies, blah, 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 or I think it thought it was against one of my philosophies. Anywho, the critical section idea was perfect. I think it's great. I just got to implement like a bit of a wrapper object that kind of does this for you, just so that it ensures that the critical section is disabled after the scope ends. And then finally, this is actually not that big of a blocker, but it would be cool if I could get the size of Pimple down. It would be an extension of Enable Strong from this, except that it actually would be a replacement. Not like a complete replacement, but if you need all the features of Enable Strong from this and Pimple, then you get that for free with Strong Pointers version of Pimple. If you just need Enable Strong in this, then you can just use that. All right, let's get into some of the port. Now, there's actually nothing too cool or interesting, in my opinion, in the V6 port for libhal-util. Everything is pretty much what you'd expect. So here we just have, actually, some of these can actually be optimized. Do I want to optimize this? I think so, yeah. I could probably actually optimize this. But you can see that things now take async future and take an async context. And then you co-await the things. And that's pretty much it. You know, just rather like the same exact code, except now we put the co-await in front and we have these return and first parameters. Yeah, there's really not much to it, really. It is simply mostly like the porting effort was mostly just copy and paste and update the return objects. And that's pretty much it. I don't think there's anything else special in here besides the fact that we removed all the USB stuff from this and we moved it into its own repo. Yeah. And then all the math and unit related stuff is mostly just the same, like literally just copy and paste it over because there's nothing, I'm not making any of these async for any reason. So yeah, nothing too crazy there. Now for libhal-arm-mcu 2.0. This is where things get more interesting. So in here, I'm actually going to go straight to the demos, go to main, and we're going to kind of see what main looks like. It's far more messy than it was before. First off, we have the import statements because we're using modules now. We have an import for HAL, util, and ARM Cortex M, or ARM-mcu Cortex M. Now, one thing in particular is that I should be able to just ignore and remove these and just import this and be fine. I remember seeing some issues, but I think that might be on me. So I kind of just did this to kind of get things to make forward progress, and then I'll go and update that later. Same thing with async context. That should just automatically come in from HAL, so there shouldn't be no reason for me to bring this in directly. It should be transited from here. ARM-mcu demos, though, that particular module is the resources list now. So before, the resource list was just a header. Now it is a module, and you import that module in order to implement its things or to use its APIs. Everything in here mostly looks the same, except now we have a pointer returning back some object. None of these return back async or a future pointer. I will very quickly and easily re-update all of these to be a future pointer if we find out that, like, you know, some of these drivers do need some time to do their work, and we don't want to do that work synchronously. Which in all cases, I think doing it synchronously would be the easiest and simplest choice. And yeah, it just imports ARM-mcu, which I don't think. Oh yeah, it's necessary for the Cortex reset. I think that's the only thing that actually needs ARM-mcu for it. I could have just actually taken this reset and thrown it into the resource list, which I could do, but not necessary. Alrighty, so let's look at the applications, and there's only a few of them at the moment. We'll take a look at Blinker, and it's pretty much what you'd expect. And this does work. I tried this on an STM, and it does the thing. Get the LED resource, co-await LED level. Now you have to pass in the context, and then pass in false, and then bada boom, bada bing, you get it's false. Next up, you then wait for 500 milliseconds, then turn true, and then wait for 2 seconds. In this case, the blinker is a bit asymmetric, which I think is kind of cool. It makes it a little easier to kind of discern. And yeah. And then UART is pretty much identical to what it was before. The read operation for UART, because this one's not an awaitable UART, a awaitable serial, which I plan to add in support pretty soon, so that we can wait for actual data to come through before we do anything. But at the moment, it just loops over and over again, writing out hello world and reading to see if there's any data available. And this part here, what is this? So the HowWrite API takes a scatter span, which, no, actually, this actually needs to be, I think, this way. Actually, it should have been oh, I see. Yeah, never mind. One way to do this would be to subspan it, but like this is just constructing a span in order to like create the span inline and throw it right in. But yeah, everything here is pretty much what was inside the previous example, the previous UART. And I think I'll show one more bit, which is ADC. And it's, yet again, nothing different, just co-wait ADC, co-wait print, and then co-wait 100 milliseconds. Now, I want to show how the 100 milliseconds is managed, how that happens. And that goes into main. And I want to make this particular waker function generic. So like all you'd have to do is pass in HAL Cortex M, Cortex M. Actually, I might even make an object for this. I might just make this an object that you can pass into this spot here. But basically, there'd be a Cortex M waker object, and it would take a sleep time, and then it would do all of the work here to schedule a timer to ensure that it wakes up at the right time. It kind of does some checks to make sure that the actual interrupt for resuming has fired. And also does the work of disabling the interrupts in order to check things and all of that. But the cool thing about this is that this coroutine can now work pretty much in proper time based on this little function that we have here. So I'll kind of walk through it. So initialize the platform like we normally did. This waker object pretty much just keeps track of whenever it's awoken, it unblocks the coroutine stack and also sets this field, this member called fire to true, which defaults to false. This is just so that we can determine, that the context got resumed or got awoken. Get the timer out, take the application, pass in the coroutine stack, and get a future back. That future can either be resumed itself, or you can actually resume the coroutine stack itself. I do need to add a sync wait to this that takes the same arguments as the coroutine stack because there is an asymmetry there. You should technically just have to work with the future and do all the work from there versus having to go to the coroutine or going to the context, but that's just kind of how I have it at the moment. And yeah, the ISR for the timer, yes. I have the waker object, and the waker object has this callback. So it's a timed callback. The timed callback, we implement the callback API. And then from here, all we do is take this global coroutine stack and unblock it. And we schedule this for the amount of time that the time duration is passed to us. So we take the waker. This is the thing that we call as the callback for when we're done. The amount of time we need to do. And also a new feature to libhal timed interrupts is the concept of a timer mode, such as one-shot or periodic. Before, I had a rule that the timer would always be a one-shot, and if you wanted to do multiple operations or multiple loops of it, you would need to have the interrupt reschedule itself. The one problem with having the interrupt reschedule itself is that there's some latency to that, and we can cut that latency out by having the driver do it. It's not a lot of work for the driver to do, and it's probably the best place to do that work is in the driver. But also reduces the amount of code that has to be implemented on everyone's side, I believe. So that's one little change. But yeah, once this thing actually is the thing that fired off and set this member variable to true, until that happens, this thing loops in here. And then basically goes to sleep. One note, though, that I noticed is that because of this sleeping action, if you try to debug your STM while it's sleeping, it'll fail. So you can just run it twice, and it usually will wake it up and keep it in a good spot where you can actually connect to it and stop the operations. And yeah, that's pretty much a little bit of a tour. If we go to the actual module side of things, we're getting some things in. We have some of the generic APIs that are already in, although they do need to maybe be touched up. Oh yeah, it's a lot of stuff in here. Independent watchdog, GPIO. This one's a bit interesting because I decided to not make a manager for the GPIO as a whole. I made individual managers for input pin, output pin, which has a create, another create, and I plan to make one for an awaitable pin, which will also have its own create function. They're split because basically the manager concept didn't really work for output pin and input pin. They can kind of manage themselves in isolation, so it made things a lot easier just to do it this way. Also, this thing does not implement Pimple because it's using the fact that the return type is a pure interface return object, or basically just a pointer to an abstract class. Therefore, all of the implementation details are hidden directly in the class underneath. So this create function has a implementation of an output pin that's only accessible within the source file. And that keeps everything nice and private. That's pretty much it. There's not really much else for today's meeting. So yeah, thank you for coming along.